So thanks to Stephen and the other organizers for the invitation. So what I want to talk about is, I think, a new observation in this area of topological materials. And it's a bit of a puzzle, which I'll get to towards the end. So I'm going to try to convince you that we are seeing edge supercurrents in this material. And these are snapshots of the data. This looks a bit like Fraunhofer diffraction, which has been done forever, right, in superconductors. But this talk's not about Fraunhofer diffraction. It's about something else. Okay, so the players here are students and postdocs from my group and the group of Bob Carver, who I've been collaborating with for many, many decades. Okay, and I acknowledge funding from various places. So I'm going to start by showing you the phenomenon. I'm going to introduce, before that, MoTe2, but this is well known to nearly everyone here. Then I'll show you the data, and then try to convince you that we are seeing this edge supercurrent. And then I will talk about our current attempt to understand it in terms of fluxoids, quantization, and then this leads to some further new results. Okay, so MoTe2 was one of the early type 2 Weyl semi-metal candidates. So what type 2 means is that the symmetry axis of the Dirac cone is heavily tilted, right? So it lies on the side and may even dip below the zero energy plane. So it's predicted from band structure to have 8 tilted Dirac cones, and they sit pretty close to the Fermi energy. There's some RPES evidence. I'll show you some of them, but the evidence is not definitive. The group of Claudia Felser found that it actually becomes superconducting under pressure. So I'm going to show a blow up of this data in the next slide. But at ambient pressure, which is what I think is the most interesting point, the TC is very low, 0.1 Kelvin. Right? So you have to get quite cold to do these experiments. And of course, many of you are involved in this exfoliation monolayer business, but we're not in that limit. I'm going to talk about 100 monolayers, or 100 layers. So this is really the bulk of material. Okay, so let me show the expanded view. So this data is from Claudia Felser's group, and you see that at ambient pressure, its TC is like 0.1 Kelvin. Then amazingly, it shoots up very rapidly, probably the fastest pressure sensitivity of TC in known superconductors, then kind of tops out at about 8 Kelvin, 9 Kelvin, and stays there. But I think when you apply pressure, you are moving the chemical potential very rapidly away from the interesting region. So there's something very strange about the superconductivity here, which, so this is the heart of the talk. Now, MoTe2 comes in 3 phases, alpha, beta, gamma. This is the gamma phase. This is the phase that's metallic and goes superconducting. And the data is very reproducible. I think that something like 5 groups now have looked at the superconductivity. We all agree that TC is 0.1 Kelvin. Okay, here's a cartoon of the tilted Dirac cones. Right, so all of you know about Weyl nodes and the Fermi arc. But when you have a whole pocket, energy is plotted vertically, sort of touching an electron pocket, they're supposed to touch at 2 points, right? And the X, the cross there, indicates the heavily tilted Dirac cone axis. Right? And this is very greatly expanded. I think this distance is only like 10 millivolts, 10 to 50 maybe. So the chemical potential is somewhere here, right? So you can see that both Dirac cones are fairly close to the Fermi energy. And I think under pressure, you're going to be moving it away from this interesting regime to a perhaps conventional metal. So what's the evidence for this? Well, okay, so RPES has been struggling for like the last 8 or 9 years. This is some early data from Condensed's group. And with mother's eyes, you can perhaps see agreement with the band structure, that there's a butterfly hole and it's touching the two electron pockets. Right? So the data is not very convincing, and people have since looked at this with very high resolution, but again, it's not very conclusive. So that's where it stands right now. Okay, so now let me move on to the observation. Right, so we cool it to way below 0.1 Kelvin, and do a simple experiment. Namely, measure the differential resistance while increasing the current to drive it beyond the critical current. Right? And this is what you see. So, the experiment is as simple as you could possibly imagine. It's a two-probe experiment. That's the exfoliated crystal. So we usually work with 100 atomic layers, tens of microns on the side. Here it's 2 by maybe 6 or 8 microns. And then just measure the differential resistance. Right? So it's quite straightforward. The IV curves, all right, so here I'm showing you the plot of the color map in the plane of current versus magnetic field. Right? Maybe it's easier to look at the individual traces first. So here I'm sitting at a constant field, let's say 1.9 millitesla, and then scanning current up this way. Right? So this vertical cut is represented by one of these traces. Right? So the system is dissipationless initially, and but if you have good eyes, you see that there's a little bit of a bump here, right? Right. So that then it remains more or less dissipationless, although now it has some finite resistance, very small. The giant step is right here, right? So here's where the system really leaves the dissipationless regime. All right, so this little bump, which disperses with a different field dependence than the big jump, traces out a Fraunhofer pattern. Right, so hope you can see this. The red curve bounces up and down with a period or frequency distinct from the fast mode, which is described by the big bump. So the big jump that signals leaving the dissipationless regime is tracing out a field dependence given by the blue arrow that is this scallop. So I'm going to be referring to the scallop profile a lot. That's what I mean, this scallop profile, right? So it's so there are two different kinds of oscillations going on. Now, let me remind you that if this were a ordinary superconductor, let's say tin, tungsten, what have you, NBSE2, none of this would be apparent. If you approach your advisor and say, I want to do this on niobium diselenide, don't even try it, because you just get the usual London equation behavior, right? The exponential screening of the current and the flux will always give you non-oscillatory dependence. So when we first saw this is a bit of a shock, and it's taken us 2 years to identify what's going on. And okay, so we are not injecting supercurrent into the material. We are not shining a microwave into it. It's just a DC, boring DC experiment in a magnetic field, right? So that's what the data is saying. To construct the color map, we programmed the computer to take between 100 and 200 traces and assemble them all with a color scale, right? So hope everyone's on board with that. Here's another sample. I'll be referring to context. Oh, by the way, the contexts are all gold, so there's no proximity effect. This isn't a proximity-driven Fraunhofer pattern, which I'm sure many of you are familiar with from experiments, for example, by Jacobi and so on. This is all gold context, right? And here's one where we have the context crossing the whole crystal. So I'm going to refer to this as a cross-beam contact, right? Because you're spanning the width of the crystal, currents flowing this way. And when you do that, you get slightly different oscillations. Now it's a mess. And you have a phase jump here, which precludes any serious analysis. But anyway, so here's another variety of patterns that we see. So there are two distinct modes, as I mentioned, and I'm going to refer to them as a fast mode. These are the ones that are running like a scallop boundary. Its amplitude is undamped as you increase the field, and the phasing goes more like absolute cosine. So it's a different phasing. This was actually a misleading expression. I'll come back to that. But for the moment, think of the phase as behaving like cosine. Then there's a slow mode, which is the familiar Fraunhofer pattern, right? Fraunhofer diffraction. I'll remind you what that is in a few slides. The amplitude decays rapidly, like 1 over b, and has a very distinct phasing. It's this sinc function, right? Sinc meaning sine x over x. So here's a more expanded view. So you notice that the fast oscillation, that's the fast mode, rings and it doesn't die out, right? So indeed, it looks like the scallop profile of the boundary. Whereas the slow mode, which has an obviously a distinct period, different period, is damping out like 1 over b. And in fact, you can fit it to the sinc function familiar from double slit diffraction shown by this green curve. The fit is pretty good beyond the first mode. The central mode seems to have been truncated for reasons that we don't quite understand. Right, and as I said, the fast mode has this cosine phi phasing. That's these two slides here I mentioned. Then if you change the geometry of the context a little bit, you can suppress the Fraunhofer mode. In this particular sample, I'll come back to the geometry question a little bit later. You have this fast mode in red. That's the scallop profile. But now you can barely see the Fraunhofer pattern. And it's shifted. I mean, now it's greatly reduced, and it's shifted up in current. But you see that it has a different period altogether. And it damps out like 1 over b. Yeah, so this is more or less showing the same data. Here is one sample where, so we notice that if we have a very large area sample, you tend to kill the Fraunhofer diffraction. There's no trace of it at all, right? So it's all dissipationless. And the moment you exit the dissipationless regime, you see only this fast mode. And as I mentioned, there's a trace of the Fraunhofer highlighted by this fit that you can barely resolve.
Why does the Fraunhofer go away for a large sample?
I'll come back to that later. We can come to geometry. Well, the basic reason is because you need phase uniformity, right? Because it's winding in the y direction.
So you figured on the
covariance line. So if you ruin that uniformity, you tend to kill it.
Okay.
All right. So let me talk about Fraunhofer diffraction. Although this is not the central interest here, but we need to at least understand the slow mode. So you don't need MoTe2, right? So this has been done now by maybe 10 groups where you can take any semi-metal, especially the ones that can be cleaved, proximatize it by injecting supercurrent from aluminum, right? So this is different now from the experiments I'm talking about, although this is data from my group. So the aluminum goes in and proximatizes the electrons in tungsten telluride, and you see these beautiful Fraunhofer patterns. Right? So that's the Fraunhofer pattern I'm talking about. That seems to be some evidence of beating, so there might be 2 frequencies. But anyway, that's what a Fraunhofer pattern looks like. Okay, so the basis is, I'm sure many of you already understand it. So if you take what's called a short Josephson junction, right, between two superconductors, and you have a weak link, but that's extended in the transverse direction, then this imitates a single slit diffraction, right? Because the applied magnetic field causes the phase, the gauge invariant phase, to increase linearly with y, as I've sketched here. Right? So it's winding in the y direction, and that causes the supercurrent to flow, in the center it'd be flowing to your right, and at the edge it'd be flowing to your left. So the supercurrent, depending on the magnetic field, can actually cancel out to give you a minimum, but the amplitude is finite, right? So you still have full amplitude. So it goes to 0 because basically it's swinging to the negative part and coming back, right? So at this minimum, the supercurrents exactly cancel. So that's characteristic of single slit diffraction, and you perform the integral across here because you're adding up all the currents, and you get this characteristic sinc function. So this is familiar from many experiments. This is more or less saying the same thing, right? So you get this sinc function, and that's the winding of the phase. Now, what I want to convey is that this is a pattern arising from the bulk supercurrent. So there are two supercurrents, one living in the bulk, because the fact that you have to wind along the y direction to generate this pattern means that it has to extend throughout the bulk. Right? But then on top of that, there's this this edge supercurrent that gives rise to the fast mode. So this is the novel feature. Okay, so for references, I'm good. So you can always measure the period of the Fraunhofer pattern, and the period yields a frequency, and we can check whether that frequency varies with area. It turns out that the slow mode, it doesn't. Okay, here's the data. So if you look at this across many samples, more or less of the same width, 2 microns, because that's the way the material cleaves, you find that the frequency doesn't change. The A phi is just the frequency, right? So I can convert the period to a frequency and then define the A phi as the flux area. And it's independent of the area. So it's basically a Fraunhofer single slit diffraction pattern. Now, I mentioned that you can actually toggle the weights of these two modes, right? You can emphasize one at the expense of the other. And so I'm going to rapidly go through that. In one extreme, you can basically suppress the Fraunhofer mode. So these are 3 examples. So this took a lot of experiments to figure out, but I'm sort of giving you the punchline. Right, so here are 3 examples. These are very large area crystals, right, as shown here. And the contacts are not cross beam, the voltage contacts. They don't extend across the whole crystal. They're more like point contacts in a Hall effect experiment. Right? And that seems to favor the fast mode at the expense of the diffraction. You don't see any trace of Fraunhofer diffraction at all. These aren't Fraunhofer diffraction because they don't have the correct phase of the sinc function. And furthermore, they hardly damp out. This one is dephasing, but here it just keeps ringing, right, all the way. Here's another example. There's absolutely no Fraunhofer pattern. All you see is the scallop profile. Again, remind you that this is what I call the scallop profile, which will turn out to be amplitude modulation, right, distinct from the phase winding of the Fraunhofer. So this is one limit. If you have large area, sites that are non-parallel, and you're in the long junction limit, in other words, the length here is much longer than the width, that tends to kill the Fraunhofer pattern. So that's the answer to your question. And the argument is that, for example, with non-parallel sites, you ruin the phase, the uniformity of the phase, and that tends to kill the diffraction pattern. But not the fast mode. The fast mode doesn't seem to care about all these factors. Okay, so this is one limit where you can suppress the uninteresting Fraunhofer mode. Here's the intermediate case where both are prominent, right? So this is a very tiny crystal, and this is the very first one I showed you, and both modes are equally prominent. Now, the other extreme, where I now try to maximize the Fraunhofer pattern, and this will tend to mitigate against the fast mode, is this situation where I'm now in the short junction limit, right? So the supercurrent has very little distance to cover. It has a transverse extension, right? So the phase is uniform across here, and then you see the very prominent Fraunhofer diffraction. So this is similar to tungsten telluride.
At the beginning of the discussion, you mentioned the Meissner effect, right? So,
Yeah.
so how does the field penetrate?
I'll come to that. Yeah. Just hold on. There are many moving parts in this experiment. Yeah, thanks for that question. Where was I? Right. So now it's so prominent that you barely resolve the fast mode, so this is the other limit. So clearly, since our interest is focused on the fast mode, we now have moved all our experiments towards the other limit. Okay, all right, so now I want to talk about why we believe this is coming from an edge supercurrent. I've shown this already, or I've shown the fast mode as opposed to the slow mode, and these are the traces. Now, if this were coming from the edge supercurrent, you could imagine expanding the area by a factor of 10, right? So this would really speed up the oscillations, and let's see if that happens. So here's the case where this sample is something like, not quite 10, maybe 6 times larger in area, and the oscillation is more rapid. And this is the other case where it's even more rapid, right? So qualitatively, it seems to scale as expected, right? So here's the plot. Across 5 samples, differing by a factor of 10, the weak field limit. So this black dashed line indicates the weak field limit when you are very close to when you're less than 1 millitesla, and it scales like the area, right? But then coming back to the point that was raised, you see this effect of gradual flux penetration. Right? Now, when you apply a field, as you increase the field, flux will penetrate, right? And there's very little pinning in this particular superconductor. So as the flux penetrates, the number of flux quanta, right, it's going to increase. And therefore, for each given sample, you're going to see the frequency, which is what A5 measures, increase as well, right? And it'll stop increasing when it hits the upper limit, which is when the field is close to the critical field. So this is evidence for what I call chirping, which I'll come back to. But now you compare this very strong linear dependence of the area in weak field with the slow mode insensitivity to the area. So the two are distinct modes. Right? So this is evidence consistent with an edge mode that flows on the boundary of the crystal. Okay, but what about chirping? All right, so now I come to this question that was raised, our magnetic screening. Now for the geometry that we have, I think the next slide shows it. For the flat plate geometry, The screening happens on what's called the Pearl length. The Pearl length simply takes into account that this is quasi two-dimensional and yet not quite two-dimensional. So the Pearl length, which replaces the London penetration depth, is given by this, twice lambda squared divided by d. So if lambda over d is very large, you can see that the Pearl length is very, very long, right? But it's not infinite. If it were infinite, then you wouldn't see screening at all, right? The fact that we have a finite thickness d means that it's large, weak screening, but you can detect it by looking at the increase in frequency that I refer to as the chirp. Anyway, so yeah, this is saying the same point, that if this were a single monolayer, a single atomically thin, then there would be no screening. Right? That's an important point. But the fact that we see screening means that the bulk supercurrent continues to screen, although in a very weak fashion, whereas an edge supercurrent does not contribute to screening. So here's the evidence. If you sit with pick any sample, as you increase the magnetic field, you see that its frequency increases and then saturates, because you're getting to the upper limit where it obviously cannot exceed the physical area of the sample. Right? So it increases and then tops out when it gets close to the upper line. So eta here is essentially the fraction of this phase area divided by the physical area. Okay, so there are two messages from this plot. One is that it does scale linearly with the physical area, but given a particular sample, it also counts the flux quanta as they come into the sample. Then you can also try to estimate the width of this channel. Right? So remember, now we are identifying it with an edge supercurrent. So we can attempt to identify, to estimate the width of this channel. If this channel were finite, it would lead to dephasing, right? Because the area enclosed would be slightly smaller, right? So within that change in area caused by the finite width, you would have decoherence. Right? So this signal will decohere at a given field. Here it's like something like 7 millitesla. And from that, you can estimate how thick you can get an upper bound for the width. Right? So when we do that numerically, you get about 100 angstroms. So these are very thin edge supercurrents that surround the crystal. So you bring all these three together, I think the argument is almost watertight. There's just no other way you can get a signal, a frequency that scales like area in both the low field and high field limit, showing the chirping effect and having a very narrow width, right? So in combination, they almost box you in geometrically. It's got to be at the edge. So that's why we come to the conclusion that this rapid ringing is actually coming from the supercurrent that is flowing on the edge. And the width, as I mentioned, is only like 1% of the total width of the crystal. Now comes the problem of how do they arise, right? What's causing it? And so here I'm going to tell you the story, the narrative is the way we thought about it and how we were misled and a painful way of doing more experiments and then finding what we believe now is the correct picture. Okay. So at first we thought that this was, again, basically the phase winding scenario. Right? If you have, well, all of you know this, if you have a Josephson ring, a superconducting ring, right, and you have a junction, either 1 or 2, usually it's drawn as 2, but then the amount of flux trapped will be quantized in terms of flux quantum, and you see the supercurrent, if you could measure it, execute these oscillations. Right? So this is usually it's implemented as the double SQUID junction, right, in the DC experiment. So you would see oscillations given by this phasing. It'll be cosine, absolute cosine pi, right? Phi, cosine phi. So we were analyzing the data for about a year using this picture. But every time I explained this, people would come up to me and say, but you don't have any junction, right? This is a crystal, there's no junction. Where are these junctions? But nonetheless, we stuck to this for a long time because this seemed to be the only thing in town, the only game in town. But one problem is the following. If you did have this absolute cosine dependence, the minimum will actually touch the zero current axis, right? And it doesn't. In fact, in all the crystals, you see that this minimum never touches the I equals 0 axis. I'll come back to this in a second. So this is clearly the wrong way to go. And all right, so here's the point, right? So when you look at the scallop boundary, sorry for the anyway, so here's the scallop boundary, right? You see that the minimum never gets to the zero current. So you say, well, maybe disorder and so on and so forth, but you never see this. You know, in the Fraunhofer case, you will see the signal reach down almost to zero and then bounce back up again. Not the fast mode, right? So this picture is actually not valid. So you have a boundary in which the minima stop high above the zero current axis. And it's independent of contact configuration. It doesn't matter in a multiple probe Hall-like device which pair of contacts you choose, you always see the same signal. You know, all you need to do is pass current and look at the differential resistance. And then finally, we confirmed the current picture by seeing something new, which I'll talk about, excitation branches. And the current picture is that it's fluxoid quantization. So I need to tell you what that is. This was found actually a long time ago by Little and Parks. So this is the famous Little Parks experiment. What they did, I should have copied their experiment here. They took this is in 1962, really early, right? They took a quartz needle and they drew it out in a flame, right? So you can get very thin quartz fiber, right? And it's only like a micron in diameter. Then they evaporated aluminum around the quartz fiber, right? So now you have a cylinder, a superconducting cylinder. And then they use this quartz needle coated with aluminum as a sewing machine. In fact, that's what they called it, a sewing machine, which they oscillated in a coil, right? So this is a very clever way to measure the magnetization. And so they can detect the transition temperature. They can see when the superconducting state sets in this cylinder. And they found that the transition temperature oscillates a very tiny amount, 1 part in 1,000, but they could measure it. And okay, so let me tell you the basis for this argument. Now, if you have a flux within a cylinder, the free energy will increase like parabolically. Why? Because when you have a field trapped in there, the superfluid velocity will increase. Right? So you would have superfluid kinetic energy, and so that makes the free energy increase until it intersects the neighboring branch. Right? Then the system will then jump to the neighboring branch and then come to its minimum again. Right? And so as a result, the superfluid velocity increases and then jumps down, reverses direction, and increases again. So you have this sawtooth profile. If the system just stays on the lowest branch, then what that implies is that the order parameter for the aluminum, the square of that will have this scallop profile. Right? So basically, the kinetic energy, the superfluid kinetic energy is a cost to the system. right? So the transition temperature will decrease when the kinetic energy is at the maximum, then it jumps to the next branch and comes down again to 0, so the TC improves again, right? So this is what the little parts experiment is. And we think this is exactly what's happening here, except we are performing the experiment in a totally different regime, right? We are going to very low temperatures, 20 millikelvin, the TC is 100 millikelvin, right? So we are in the very low temperature limit where the order parameter is fully saturated. But now we are applying a large current to kill the order parameter. And then we're seeing this appear. All right, so this I hope will become more convincing in the next slide. So we are doing this, we're repeating the little parts experiment, not using temperature to kill the order parameter, but using a critical current to kill it, and therefore we're seeing this at very low temperatures. Oh, the quantization, the fluxoid quantization is given by this velocity, which has this sawtooth profile. All right, so sorry for all these equations, but this is really very simple stuff. This is basically Ginzburg Landau theory. So as I mentioned, we are going to very low temperatures, and the bulk and edge amplitudes have achieved the equilibrium maximum value, right? Which I denote by this 0 subscript. Now, when you add a magnetic field, the magnetic field doesn't contribute to the free energy of the edge mode because it's too thin, right? It's almost one-dimensional. However, it increases the kinetic energy of the superfluid, and that is incorporated by this 1/2 mv squared. Right? So these are the familiar alpha beta terms of the Ginzburg Landau expansion, appropriate for the edge mode, right? This is Fe will always refer to the edge mode as opposed to B, that's the bulk. Then you combine these two terms together, and you see that you basically renormalize the alpha term with the kinetic energy. Right? So all of you know how to do this. You minimize that, and you get the new amplitude to be given by this replacing alpha. But now the velocity squared is given by the fluxoid quantization. So ultimately you end up with this. So the fractional change in the square of the Ginzburg Landau amplitude for the edge mode is the negative of the free energy. Right? So that's what you end up with. This is the expression for the scallop mode. But of course, we don't measure this experimentally. We measure the critical current. But the critical current, leaving details aside, will be given as proportional to the square of the amplitude for a bulk superconductor. So by measuring the critical current, you're essentially picking up this scallop potential. So that's the gist of the argument in terms of the coherence length, the Ginzburg Landau coherence length. But can we get more out of this, right? So this is fine because you already know the data, you know all the properties. Is this a useful picture that can make predictions that will help you understand more about what it is you're seeing? So this is the last part of the talk. I think I'm going to end pretty early. Okay, good, that's good. All right, so I've shown this before. So this is the rapid ringing that we're interested in from one of the bigger crystals. And now we're going to zoom in here and take it at very high resolution. These plots take a long time to construct, something like 24 hours. But we're not going to slow down the acquisition rate by going to very high resolution and look for new features. And this is what we see. All right, so it's the same sample. The yellow scallop profile is one branch of this, right? So I think it's sitting way here, out here. But now at this higher resolution, you see something new. I don't know if you can see it from the back, but you can see these branches trailing off, right? And they start off at the minimum of the scallop profile, of each minimum, and they trail off in one direction. Right? The green dots are fits to the equation. I should have reproduced it here, sorry. Let me remind you what the equation is. Of this equation, right? Basically, it's just the inverse of the parabolic behavior, the inverted parabolas. So these are the parabolas, right? But we only see one branch. Right? And to convince you that it's really there, I'm showing some individual traces. So you see so this is in a very narrow current range from here to here in a field scale, a restricted field scale, right, over this part. All right, so the big jump, as I mentioned before, this big jump is tracing out the scallop profile, right? That's the main feature that signals when you're leaving the dissipationless regime. But you can see that there are these tiny little bumps that trail off, right? That's shown in blue. So those are the tails that correspond to the transition, to the excitation branches. So this data would be totally incompatible with the double junction SQUID model. So this is a big influence on our thinking, that you see this, which is impossible to account for by using the double junction SQUID. Here's another sample to convince you that this is not a fluke. This is sample S2, and you can see, again, maybe not as clear as the other one, that there are these branches that trail off the minima of each of the of each minimum of the scallop profile. Okay, so here's how we understand it. Remember, the free energy has many branches, right? Each one of them is centered on a integer number of flux quantum. Right? So as you increase the field, the system likes to sit at the minimum, or it likes to trace up the minimum of the curves, and it will jump when they intersect, right? So let's say that you're sitting at the dashed line at exactly an integer number of flux quantum. That is your ground state. You're happy with this, right? But you notice that at this field, you can still see the excited state, which is the previous branch, if you were coming in this direction. The previous branch, but now with the wrong number of flux quanta, right? So if you capture the wrong number of flux quanta, you have a higher velocity, the superfluid velocity, which is doing the screening, will be much larger, and therefore this is a costly, it's an excited state. It costs more energy, right? Now, this hasn't been discussed before because no one has ever done little parts experiment at such low temperatures. And so I think that's why this is showing it. As I mentioned, you invert the free energy curves to give you the square of the Ginzburg Landau amplitude, which can be translated one-to-one for the critical current. So this curve here is the scallop potential of the critical current. Yeah.
Maybe I'm misunderstanding something, but how are you observing these excited states if your acquisition rate is so slow? So like,
If you
what's the lifetime of this excited state? Because you said it takes 24 hours to.
We don't know the dynamics, yeah, because these are all equilibrium experiments, right? So the way we, that's actually a question that we have struggled with. So this is a dissipationless regime, right? So when it hits this state, right, it's as if you were seeing a burst of quasi-particles.
Okay.
So it's steady state. It's not a
Steady state.
it's not a pump probe type experiment.
Okay.
Yeah, it's a steady state. So you have a burst of quasi-particles, and then they go away as soon as you exceed the branch. So yeah, there's some microscopics that will have to be ironed out. But anyway, the data is there. You know, it's you really see it at steady state. And these are all DC experiments. But anyway, okay, so yeah, while I'm making that point, as you scan up, right, and you hit this little bump here, that's equivalent to what I showed here. So we are scanning up in current, remember, vertical axis is current, and then you hit that little bump. Why the system is telling you that there is an excited state, we don't know. But I think it's exactly this scenario because all of them are doing it, right? So every branch that they cross, they see it. So there's a burst of quasi-particles, and then it doesn't really increase the dissipation at all, much or not much at all. And then you hit the wall here, where everything goes. You get into the scallop boundary, and then there's a big jump in the dissipation. Okay, so that's our working model. That it's we're seeing an excited state with the wrong number of fluxoids captured, and this seems to me, anyway, rather convincing evidence that the fluxoid picture is the correct one. But then immediately you run into puzzles, right? Why aren't we seeing the other branch, right? Because this one is coming down. We should see both, right? And this is a symmetry problem that we don't really understand. So I'm showing you here it is. So if the field is negative, you see all these branches rather clearly, right? But the other ones that are flowing this way are conspicuously absent. But now if you reverse field, you see that, I don't know if you can see it, they're all following this as well. But now the other branch is starting to appear. So this is a possible competition between the applied field and the intrinsic chirality, if you wish, of the system. If you reverse the current, you will see quite the opposite. So this one will be equal to the other current. Is that my phone? Someone's talking to me. Let me see. Okay. All right, so these are the symmetry problems. For a given field, half the branches are missing, right? The ones that are flowing to your right towards decreasing field magnitude are conspicuously absent. And the one rule that we could come up with is that if I cross B, it's like a Hall effect. It is negative, then the branches flow towards increasing B. And so you can switch the sign of B or the sign of I. If you switch them both together, you will see the branches. But then in the other two cases, which is this and the one that I didn't show, it's less clearly resolved. Okay, so this is a puzzle that's revealed by the excitation picture. And I think that brings me to the end of the talk. So in summary, we see these oscillations in the critical current that we think are arising from edge-confined supercurrents. There's a fast mode and a slow mode. The slow mode is, we think, conventional, just a Fraunhofer diffraction. The fast mode is the new feature, and we interpret it in terms of fluxoid quantization. And from this picture, actually, we can anticipate the excitation branches, but then they reveal this interesting symmetry that still is an open question. Okay, thank you for your attention.
Thank you, Professor Ong. Are there any questions?
Did you study this effect at different temperatures? Because it seems that closer to TC, the suppression will be more dramatic.
No, somehow the phase coherence is important. Once we warm up significantly to 50 millikelvin, it's very hard to see it. The TC in these materials is not sharp. You know? Just like twisted bilayer graphene, the transition to the superconducting state occurs over a very broad region.
So with your original sink fitting to these slower oscillations, it accounted for like the damping that you see as you went to higher field.
Yeah.
But we also see like this decrease in the fast oscillations, right?
No, the amplitude doesn't decrease. The
But like
frequency,
the position at least does, right?
the position.
If you like go back to
Ah,
your,
yeah. Oh, no, I think, yeah, that's
these
the,
things all have a slope. Can you
you,
account for that?
you talk about this decrease? Is that what you're referring to? Which
just
decrease?
that like all your like
Oh, let me show.
theoretical models for that were of like, yeah, they all progress flat, right? If you, those things,
Yeah.
they're horizontal.
Yeah.
Whereas your experimental plots all have some slope.
You mean the slope?
Yes, that's slope.
No, okay, yeah. So this is the, now let me bring up a better picture. This is the critical current, the magnitude of the critical current. On top of it, there is this modulation. The amplitude of the modulation doesn't change. Actually, I didn't go into this in detail. When you pump current into the crystal, the current is shared between the two supercurrents, right? It's got to be because they're parallel channels. But the bulk will take the lion's share of the current, right? Until you apply a field. Once you apply a field and you drive the system close to the critical current, then the edge mode is going to be increasingly important because it's immune to field suppression, whereas the bulk is really crashing, right? So that's why when we get to the edge, so if you're at zero field and zero current, the lion's share is carried by the bulk, but as you approach the boundary here, the edge becomes increasingly important. And that's why it picks up this scallop potential.
Hi. Thanks for the great analysis. I think it's convincing now. One question is, in Little Park experiment, you don't have contacts. Here you have a current go from contacts one to the other. How can you comment on this? How
Yeah,
contacts
it's the same
involved?
point as I was just mentioning, right? So if you inject current, then the current is going to be carried by the bulk supercurrent, mostly. But some of it's going to be also carried by the edge, a very tiny fraction.
And the current will kill the bulk, not the edge, and you choose
Where
one edge.
if you keep increasing the current in a magnetic field, right?
Yeah.
So that means you're moving in this direction. Then the bulk is going to be decreasing in its Ginzburg Landau amplitude much faster, right? But the edge is immune to magnetic field. So an increasing fraction is carried by the edge current. That's why you start picking up this scallop profile. We view the conductivity measurement as simply a probe of the edge current.
When you discuss the edge currents, this somehow suggests a two-dimensional picture with one-dimensional edge. How would you think a finite thickness?
No, good question. We think that there are 100 layers, so the edge current is actually on the side wall.
So there is some dispersion also in z direction of the side.
Perhaps, yeah, but there's only 100 layers. Yeah, probably, yeah. So there are 100 modes. It cannot be two-dimensional because, as I stressed, the two-dimensional, a single monolayer will not have any screening at all. And you won't see chirping, you won't see the flux penetration phenomena. It's got to be finite thickness.
So you mentioned we don't need to do this around Namian for example, but those other
But I don't want to discourage you. You feel free to do it.
So what I mean, how this reflect the intrinsic material? So how that is related to the materials?
So there are speculations that MoTe2 can have either Fermi arc states or in the beta phase, even hinge states. So if you have hinge states, you may have these edge modes. The trouble is the band structure, if you trust it, the hinge state only exists in the beta phase, which is insulating. Right? So it's totally open question.
Are there any signatures of these modes in the normal state? Is it possible to convey some
These are supercurrents,
Sure, but in the normal state.
normal state. You mean above TC?
Yeah, above TC. Can there be any hint that can tell you that
Ah,
there is
okay.
a side fault?
We don't have any data for that. Because once you go above 100 millikelvin, everything is normal, right? So then the question is, are you sure that near TC, it's actually being caused, the TC transition is caused by the edge? That's, I guess, your question. Right. Yeah, but the trouble is these experiments are hard to push above 50 millikelvin.
Okay, let's thank Professor Ong again.